At this point, maybe I will quickly recap what we have seen. So we introduced NLP. In particular, we look at some tasks in NLP. We saw that we have various groups of tasks. But one interesting thing is that we were able to mostly use the same model in all these tasks, and this will come in handy in the last point that is called BERT here. And we said that, okay, we have several tasks, but one common issue is to find the relationship between words and semantics. We always need to do this when we are dealing with NLP tasks. And in order to do that, we mentioned two ideas that can guide us, the principle of compositionality and the distributional hypothesis. But then we started to look at how we were representing words and sentences in classical approaches. And that means one hot vector, so that's how we were representing words. So this vector where everything is zero except one element. And then we show that there are disadvantages with that. In particular, the vector will become huge if I have a very big vocabulary size. And the other disadvantage is that it is not capturing any semantic at all, because all the words, they are at the same distance in the vector space. And then we also saw how to represent sentence, and also that representation, which was called bag of words, had some disadvantages. Now let's see how we can create a better representation for words that hopefully is capturing some semantics. So first, let me say that the one hot representation that we saw before, that is called a local representation, because basically it's just doing a one-to-one mapping between a word and a position in a vector. So again, we saw that the one hot was mapping into a vector where everything is zero except one element. And that position was really giving me the information about which word we are talking about. And again, so these are the disadvantages that we mentioned before. In particular, the vocabulary size, it can be problematic here. It may be that one word, just dog, it may be that to represent this word, I need this huge vector of 80,000 elements. So you can see how this is definitely unfeasible to handle for the models. The second problem, again, there is no semantics at all in this representation. Again, you see this plot, and all the words, they have the same distance, so I'm not capturing any relationships between the various words here. So let's see a better solution. So a better solution is basically, it's what we call a distributed representation. So a distributed representation is different from one hot in the sense that while in one hot we were just using one element in the vector to tell us the meaning, in the distributed representation we use all the elements in the vector by assigning some values to all the elements, and somehow this is giving us the information about the semantics of that word. And this is called distributed because I'm distributing the information over all the elements of the vector, which was not the case with the one hot representation. You can see this with an example. So let's say that we go back to the previous example where we had cat, dog, house, and PC. And now the representation can look like this. So you see that instead of having all zeros and one, we now have values. These values represent some things that for now we don't know. But the idea is that is to obtain something like in this vector space here. So you see that now dog and cat, they are vectors that are closer than, for example, dog and house. And now I can use this freedom of putting the vectors the way I like to really capture the semantics of the words. And another interesting property that you can see here is that I have 4 words, but I decided to represent these 4 words with just 3 values now. And now I can do that. So now I don't have this constraint anymore that vocabulary size equals vector size. And in fact, what usually happens is that we will have a vocabulary size of maybe 100,000, but the vector size will be around 300 or 500. So it's much smaller than the vocabulary size. And still, it will be enough to capture all the interesting information for the words. So the interesting thing is that for now I still, so we know what are distributed representation, but I'm not telling you now how to create them, so how to come up with the values in the vectors that I showed before, and we will see that later. For now, let's look at how we would like this distributed representation to be. In particular, we would like to have two interesting properties. The first one is that semantically similar words, they should be close to each other. And the second one is that we would like somehow to capture the relationships between the words, because again, this is very good information about the semantics of the words that the model can use. So let's focus on the first one. So here you see a plot of this distributed representation. And the interesting thing is that you see that we have some clusters which are colored differently. Like here you see a yellow area, and you see that I have words with a similar semantics. I have a refrigerator, I have an oven, a microwave, and so on. So stuff that, tools that I can find in the kitchen. Here you can see that I have a bath tube, a bathroom, so tools that I can find in the bathroom. And yes, it is not perfect, but you can see how this representation is much more informative compared to before. And the second, so here you see how semantically similar words, they tend to be represented close together in this space. The second problem, a characteristic that we would like to see in this particular representation is that they somehow capture relationships between words. So here you see this relationship between country and capital. And you see all the countries here on the left, and you see the capital here on the right. And even if it's not perfect, you see that we have this with this pattern, where basically we can go to the country, to the capital, from the country to the capital by applying this vector. And again, it's not perfect, but you see how this representation is interesting, because now the model is able to build on top of this information to solve the task that it's trying to solve.